Welcome. This little lecture comes with a preface. About 32 years ago, maybe a little bit more, I fetched up in a job in a university in which the department, it was a philosophy department, was famously riven with hostilities, let's say. And there were political hostilities. And between, as it were, the left and the right, let's call them that. This was a sort of tricky situation to navigate. So in typical fashion, I decided to give a talk to a large group, which was titled, "Why the Left and the Right Are Equally Wrong." You may say that was a risky thing to do, and you'd be right. At any rate, I did it. And I'll give you the results at the end of the talk. Most interesting. So I didn't publish it subsequently. So this is the second outing it's ever had. Why the left and the right are equally wrong. Provably wrong. Okay, the first thing I want to do is to tell you what a random walk is. It's something in probability theory. It's something in the theory of stochastic processes. I want to give you an idea of what it is, because everything depends on it. So a random walk is, I'll give you a visual example of it. Suppose you're tossing a coin and you're taking account of whether it's heads or tails. So a random walk of this kind is given, suppose we say heads is +1 and tails is -1. We start recording it. So we start here, and we record the results. So the first step is heads. The second step, the second toss of the coin, is heads. So we've got the numbers of the toss here along the bottom, and here we've logged the results. So we've got heads, then we toss the coin again, we get tails, that's a toss 3. Then we get heads again, and then tails and tails. And that takes us back to the origin. So you can see heads, tails, tails. Right. So you can look at that and you can say, well, to get back to the origin, we need an equal number of tails and heads. Fine. This is the result, and this is the zigzag that we get. Okay. Now, this is an example of a random walk, because it's random, because it's simply the curve, or the zigzag follows the outcomes of a random experiment, in this case the tossing of a coin. Okay, and this is the equilibrium point. So in other words, if we get back to the line, then it's called equilibrium, which means we've got an equal number of heads and tails. When you can add them up, 3 tails are there, 3 heads are there. So we have gotten back to the equilibrium. Much of what I'm going to say has to do with the divergence from the equilibrium, can be positive or minus, the divergence from the equilibrium, and where the equilibrium points come in a random walk experiment. Okay, that's it. That's the background you need. That's all. Now, suppose that we say, in a sort of sociological way, that everyone is intrinsically equal. They have no more or less talents than anyone else. They all have the same talents. They're all born with the same talents or abilities, however you want to say it. Right, so we're going to subject them to an experiment in which the outcomes of the experiment are just due to chance. So then there'll be, if we were to think about this intuitively, what we would expect is, well, they're all equal. We've got a certain number of equal participants. They're all being subjected to their own chance random walk. What's going to happen? Well, some will be, what we think is, some will be ahead and sometimes, and some will be ahead and other times. And that lead and who is behind is going to change in a sort of more or less continuous way. Why do we think that? Because our intuitive response is to rely on something that is called the law of large numbers, or the law of averages. What we think is that, well, on the law of averages, that's what we'll call it, on the law of averages, someone is bound to be ahead at one point, but then someone else is going to catch up and they're going to swap. And so they'll move, as it were, from one side of the sort of the neutral equivalence line onto the other. And they'll change randomly, and they'll change quickly, we think. So start them off with exactly the same abilities, dispositions, and they will move to the other side of the zero line, equilibrium line, frequently, and we won't see anyone, as it were, dominating anyone else. What we're going to see is they start off equally, they're going to continue equally. And if you go on forever, then they will continue swapping a little bit and, but basically continuing equal, because the random walk is not going to make them different. They're all subjected to the same test. They're all just simply being subjected to a coin toss experiment. So they'll change sides, but it will stay the same. Start equal. They're equal in the middle of the experiment. They're equal further on. Continue it as long as you like. Law of large numbers, the law of averages will mean that they stay the same with minor adjustments between them. That's our intuition. It's a fairly good intuition, it seems. We rely on it in many, many different ways, many more ways than I'm going to talk about here. So that's, as it were, one part of our idea, and it's people who start equal, subjected to nothing other than random chance, will continue equal for infinity. Okay. Now, that's one idea that is part of our social thinking, and it's been the cornerstone of social thinking for well over 100 years now. That's the cornerstone behind the idea of revolutions. What is a revolution designed to do? Well, the optimistic way of thinking about a revolution is that if we take away all of the unfairness that has littered people's lives and has caused them to be in very different stratas of society, given that intrinsically they are all equal, the shake-up should set that aright, and we should get this utopia of small differences continually changing our fortunes, but not in any major way. That is the basis of left-wing thinking. It has been for a long time. It was sort of there in the beginning of probably the French Revolution, was probably there also. In fact, it definitely was there for the, say, Russian Revolution, for example. So it's an optimistic idea, and it seems eminently fair. Change the fortunes, then equal people will remain equal forever. That's the principle. Okay. Now, it's also, oddly enough, the cornerstone of right-wing thinking. Exactly the same principle is the corner of right-wing thinking. The right wing has a different interpretation of it, but underneath it, it's the same principle. So people who are right-wing are often, plutocrats, and so people who have done very well in life. Let's imagine that group, say bankers or traders or whatever. They will sit around perhaps and congratulate themselves for being winners, very, very wealthy. Why? Well, because the pluses and minuses are sort of a random thing, but they say to themselves, because we're so far ahead, we must be incredibly superior. We can't be equal to the other people. Were we equal, then there would be no difference between us. I wouldn't be superior to them. I would be no better than any of them, and we would have the same fortunes. And sometimes I would be ahead and sometimes they would be ahead. But we see that that's not the case, says the right-wing plutocrat. Because of the fact that I am ahead in this game, and I've been ahead for a long time, I must be intrinsically superior to them. So, the one principle underpins both of the ideas. And if you examine it logically, what you can see is that the thing that underlies the left-wing view is, if all is equal, then it will remain equal. The thing that underpins the right-wing view is that if things are not equal far along, then it's because they weren't equal at the beginning. And if they weren't equal at the beginning, that must be only because I am superior. I won in this game, they didn't. That shows that I am a superior individual to them. They are plebs. They are the hoi polloi. They are undesirables. They are, use your own imagination for another euphemism for it. Okay, or not a euphemism, a term of insult. Okay, now, those two things are, by the way, equal. If A, then B is equivalent to, if not B, then not A. The way I set it up, if A, then B is the underpinning for the left-wing view, then if not B, then not A is the underpinning for the right-wing view. And those two things, if A, then B, and if not B, then not A, are equivalent in logic. So they're both appealing essentially to the same underlying position. It's just expressed in one way positively, and another way contrapositively. Okay, now let's see what happens when we apply some probability to it, to the random walk idea. Suppose we have 10 people and they put on headphones and they each have, we're going to be looking at random walks for each one of them, a different random walk for each one of them. Each one of them, in other words, is going to be subject to a random fluctuation that is given by the toss of a coin, or rather 10 tosses, the tosses of 10 coins, and let's see what happens. Remember, what we expect is that they're going to be very similar to one another. They're going to simply move from being ahead to being behind randomly as we go on. There's not going to be any great difference between them. Okay, now we're going to have a finite number of coin tosses, and it'll be fixed to this regimen. We're going to have a lot of them. So each of the people gets their own series of tosses of a coin, fair coin. All of them, in all these cases, the coin is fair. So we're going to have them subject to coin toss, and we're going to have that one every second, every day and every night for 1 year. So each of them is going to be subject, the headphones on, they're getting the results of a series of plus ones and minus ones, which are going to be the graph, the graph of the random walk. Okay, and as I say, we expect them to not be very much different from one another. Very similar, very, very similar in fact. That's our expectation. What happens? So we've got the random walks going for once every second, day and night, for a year. That's a long trial. What happens? Well, completely contrary to expectations, this is what happens. One of them will have its last equalization. Remember, that's the last time it goes to the equalization point, the equilibrium point on that graph. So it touches that 0 point. We'll have that in the first 9 days. One of them will have the equilibrium point in the first 9 days, or equalization point, we can say it. That's in 1 in 10. In 1 in 10 cases, one of these 10 individuals, the equalization point will be in the first 9 days. Suppose we had 20 and ranked them against one another. What would happen then? Less or more? Well, then one of them, in that 20, would have the last equilibrium point in the first 2¼ days. In other words, that individual would be behind for the first 2¼ days and ahead every moment after that. If we have 1 in 10, one will have the first equilibrium point in 9 days, and after that, it will be ahead for the rest of the year. If it's 1 in 20, it will be 1 has the equilibrium point within the first 2¼ days, and then it is ahead for the rest of the time. Ahead in the sense of ahead or behind. We can make it either of them, depends on how we're betting. It will be ahead or behind for the first for the rest of the time, except for the first 2¼ days. If we have 1 in 100 subjects doing the test, then it will have its first equilibrium in 2 hours and 10 minutes. And for the rest of the year, it will be on one side, I'll put it this way, on one side of that 0 equilibrium point. 9 days for 10 subjects, 2¼ days for 20 subjects, 2 hours and 10 minutes for 100 subjects. It will be ahead, and just in the same way, someone else will be behind in that same frame. So what you see is that being ahead or behind, in other words, being on the one side of that equilibrium line, occupies almost the entire year for just 10 subjects, even more time for 20 subjects, and even more for 100 subjects. So in other words, if we start off our cohort of people, say we have a class, and we subject to them all to an experiment, maybe they just have to sort of colour dots or something, but it's in a random way. And suppose there are only 2 outcomes, and they're both equally likely. What we would think if we ran this experiment is that we had one genius who's ahead for almost the entire time, and one who's a bit of a laggard, who's behind for the entire time. And we would judge them just in that right-wing way. We'd say the one who's ahead must be so talented, must be so above his peers that they're not his peers, they're undesirables. He is superior to them. That's what he would think. If we look at it from a left-wing perspective, all of this would be completely bizarre. We'd think, well, someone's cheating. Put them up against the wall because someone is clearly cheating in this. They have too much. They're cheating. But no, they were subject to a random walk. All of them in this discussion have been subject to random walks. Now, you might say, well, surely some of them are going in that way that we expect. The law of large numbers is just going to give at least some of them, at least they're going to just oscillate around the equilibrium point. So that must surely be true. Some of them, most of them, whatever, however we want to say it, no, even that's not true. In fact, oscillating around the equilibrium is the least likely outcome for all of them. The most likely outcome is that occupying the extremes, being on one side for almost the entire time or the other. That's surprising. Very, very, very surprising. And it took many probability theorists a long time to accept it, but it started coming out in the 1930s. It's called the arc-sine law, and it came out among probabilists as a result of the work, I think mostly initially under the work of Paul Levy around 1939. And it was refined, and calculations were made to see whether this could possibly be true, and it is. The work was refined by a probabilist by the name of William Feller, F-E-L-L-E-R, William Feller. So that is it certainly is contrary to our expectations, contrary to our intuitions by a long way. And given that it's the mutual, the one shared assumption between the left and the right, the law of averages, in the way that I described it earlier, because that's the shared assumption, they're both equally wrong. If we show that one assumption is wrong, then they're both equally wrong, and they're wrong for the same reasons. They're using the same underlying logical principle, in order to bolster their views. One for a sort of an extreme prejudice in favor of oneself, and the other one for an optimistic idea about what would happen if we were to take everyone's property and everyone's livelihood, and we were to set them all equal in a 1984 fashion, all wearing the same clothes, all doing the same thing, everyone just subject to some kind of random experiment. Well, what would happen to them is that they would diverge. Some would end up ahead and some would end up not ahead. Let's just put it that way. So, both equal. There are many applications of this idea. Some of them go back even into the 19th century. One of them is called the ballot paradox. It goes like this. Suppose you have a ballot that's being run, say, because it's contemporary with my doing this today, it's up foremost in the mind. Suppose you have an election for a president of a country. Suppose that you're making your count, the count of the winning and losing in this two-horse race. Suppose that halfway through the counting, one subject is ahead and has been ahead for quite a bit of the counting thus far. You're halfway through, but they've been in a solid lead for a while. How likely is it that that lead is going to change suddenly from that point onwards? You're halfway through the counting. How likely is it that it's going to change? Well, let me tell you, it's extremely unlikely. It's 1 in a billion chance that it will change after that point. Interesting. Interesting that is almost impossible, in probability terms, for that to change. Now you may say, what is the underlying logic of this? Well, it's this. Once you've got your random walk and you're ahead, suppose you've been ahead for a while, then these crests are going to be very, very far from the equilibrium. You've had a lot. You've been going on for a long while. You're a long way likelihood is that you're a long way now from the equilibrium point, and you're halfway through, say. How can you get back? Well, you would have to have not just an equal number of the opposite ones, but more in order to get back to the equilibrium point. So when we start off here, we're only 6 out from the equilibrium point, and we cross it at time 6. So what we need to cross that equilibrium point is more of, as it were, the ones that weren't coming up in the heads and tails thing. And we have to have more of them. So getting to the equilibrium point, once we've been away from it for a while, becomes harder. That's it. Just as if someone is ahead in a ballot, then it's harder for the loser to make up that gain that the other one has, to make up that difference. They'd have to not only make up the difference, but they'd have to be beyond it. So it's harder for the loser, the one who's losing in this process, to get on the other side of the equilibrium line. That's it, and that's all. So this also has applications to genetics, because there you have random mutations as well, and they are random. In this case, it's a more complicated affair. What genes are mutating and what are not can be subject to forces, for example, radiation, etc. But the idea is the underlying idea is very similar. The mutation itself can be forced, but how it mutates can be regarded as a sort of random matter. Okay. Now, let me not make this too long. So what I'm going to do is just show you. I can't give you much more of an idea of the background idea than this here. I just wanted to tell you about this because it's so stunning, and stunning for professional workers in probability theory. The person who did most of the work on this is a probabilist by the name of William Feller, as I mentioned before. This book has 2 volumes. It's called An Introduction to Probability Theory and Its Applications. It's been called by one of the leading mathematicians of the 20th century one of the most important books of the 20th century. That was Giancarlo Rota. Giancarlo Rota said that. And the book, so you can find it and you can work through the chapter 3 itself, that's where everything is in. An Introduction to Probability Theory and Its Applications, Volume 1. Volume 2 also has things in it, but this is mostly in Volume 1. 3rd edition, revised printing. 3rd edition, revised printing. That's what you need if you want to get onto this idea. Think about it. Think about more applications of it, because there are applications also to physics, because physics, remember, is also governed by some random fluctuations. You can find it there, and you can get the book for nothing. You can't own it, but you can at least look at it. You can borrow it from the library, which is called Internet Archive. Internet Archive will give you the book, chapter 3 of that book. Remember, only 3rd edition revised printing. Revised printing made corrections on the 3rd edition. And you can look through it yourself, and you can, well, in this case, educate yourself on something that is truly fascinating. But I think the most important thing is the false principle of relying on the law of averages or the law of large numbers is an endemic fallacy in our thinking. What's the core of that? Why is it a fallacy? Because the law of large numbers is what happens if you have an infinite random walk. What happens if it's infinite? You've got so much time then, an infinite amount of time, for your random walk to cross the equilibrium point over and over again, an infinite number of times. So it averages out to a half. That's what the law of large numbers says. If you take that crossing of the equilibrium point, you've got a probability of a half of it being heads or tails. That's it. Now the mistake, the crucial mistake, is thinking that what happens in an infinite run is the same as what happens in a finite run, and it just isn't. The finite random walk is a very different beast than an infinite random walk. You can't toss a coin, in this case. You couldn't toss a coin for infinity. You'd wear your arm out. But you can toss it for a finite number of times. You can get a machine to do it. You can just simply get a random machine to spew out plus ones and minus ones, which would be the same thing. So a random generator of that form would be fine. It can't be a random generator of an infinite number of this, because it would wear out. Now, that practical issue of it wearing out is not really the main point. There's a huge difference between the infinite and the finite. Huge difference. And I must say, and this is going to be, as it were, against my own folk, that philosophers themselves are incredibly immune to understanding that what applies in the infinite case is not necessarily what is going to apply in the finite case. In fact, it's almost certainly not. But philosophers find it very hard to grasp that, and many of the probability paradoxes that they tinker with and put in front of students are not really paradoxes at all. They're just the result of them not understanding the difference between what happens in an infinite case and what will happen in a finite case. Anyway, that's my own kvetching against philosophers of probability. For the most part, they're just wrong. Okay, well, I said I would say what happened when I gave this talk. Just showing up in a department that was riven and had been riven for years through this division between the left and the right, and had created this thoroughly toxic environment. What happened in this talk? What became of this? Well, there were two very different reactions. On the left, who very courteously, I thought very generously, had turned up to the talk. Very different from the reactions of the right. Take a moment to think what the difference between those two reactions were. I'll even give you time to write it in the comments below. What were the reactions of the two? Well, I'll tell you. The people on the left were absolutely infuriated. They were up in arms. The people on the right were also unhappy, but in a completely different way. They wanted to know, what I hadn't actually told them by that point, they wanted to know, what is the difference here? Why does it work? How do you get the proof of that? And I gave them a little an encapsulated version of the proof, and then I put them on to Feller and other books on stochastic processes, which one can also hunt down and find. You'll find it probably under the heading of what's called the arc-sine law. So when it was done by Paul Levy in 1939, the title of these various proofs were under the heading of arc-sine law. That's ARC-SINE, the arc-sine law. So they were just curious as to how this could possibly be the case. Well, that was the difference. So that was an interesting adventure of giving a talk on this political topic of left-wing versus right-wing ideas. I never published it. I didn't write it down, and I never repeated it. But I didn't repeat it because I was afraid of the reactions of people. That's not true. I didn't mind that at all. I didn't give it again because the truth was, having given the talk, I'd intended to sort of give it so that I could see for myself what I thought about this. I could run the argument through and see whether I believed it or not, whether I could see a problem with it. And I couldn't. So I didn't ever have to give it again. I had convinced myself, and I've had the same view ever after this. I don't agree with either the left or the right. They're both wrong. They're both mathematically unfounded. They can't be defended. And life and the world is completely different to how they and all of their minions all over the world with their ideas think the world works. Is there a way out? Well, not out of the theorem, but the only way out is to deny one of the premises. It's simply not the case that if everyone starts equal, with equal dispositions and with equal abilities, that they will end up the same. It's just simply not true. Now, if you may say, well, what happens if everyone's not equal? Well, then they'll end up differently, same as before. If they're different in some way, then probably, but not certainly, those abilities will lead to them being ahead. There's nothing wrong with that. If someone is superior in some way, say in making money, then they'll probably be better at it. That's all. That's all that follows. So if you deny the premise, then you get a very different result. It's just the obvious one. Different abilities give rise to different outcomes. That's it. That's almost certainly true. No amount of random life events can make that false. It's not necessarily true. It can be false. That's the answer. It can be false. The less able can rise to the top. Those who are able may not. It's a sad truth, but it's true. And you can't tell by someone's coming out on the top that they are a genius, that they are wonderful, that they have abilities that no one else has. That is false. Completely false. No one who has done well should pat themselves on the back for their doing well. Many people who do well don't do well because they have superior abilities either. They do well because their circumstances were beneficial to them. Good family, good school, all the right connections, and so on and so on and so on. That is the other sad truth of this. That's something you can count on as a factor in the fate of people. Okay, that is it. Think hard on this because it's a big life lesson. So big that it's almost unthinkable how much it matters. Okay, that said, look forward to seeing you next time.